Point forecasts provide only a single value of the expected wind or solar power production for each future point in time. In this lesson, we'll focus on wind power, but the same principles are used for solar power. Errors in measurements and meteorological forecasts will end up in errors in the wind power forecasts. We want this error to be as small as possible. Other factors affect the forecast accuracy too, also because it's a complex system. The total system, consisting of a large number of wind farms and meteorological forecasts, will inevitably change over time since the population of wind turbines changes and some characteristics are difficult to model directly. One important example being the dirtiness of the blades or PV panels. A state-of-the-art wind power forecasting system must be able to handle these time-varying characteristics. An adequate forecasting system may use adaptive and recursive estimation to handle these issues. This is described in Chapter 10 of my book, Time Series Analysis. A typical tool consists of a static wind farm power curve, models for the dynamics, and models for aggregation to larger areas. A wind turbine power curve describes how the wind power production depends on the wind speed at hub height. However, for a wind farm, the layout of the farm plays a very important role, and the wind farm power curve depends on both wind speed and direction. Also, the meteorological wind speed and direction may not be at hub height. To overcome this problem, statistical procedures are used to scale the wind speed and direction from different heights. A wind farm power curve can be modeled using non-parametric or conditional parametric models. You can read more about these models by consulting the references. The structure and number of parameters of the dynamical model depends on the prediction horizon. For short-term forecasting, autoregressive models are very important. See, for instance, my book. For very long-term forecasting, seasonal components and a dependency on the static wind farm power curve is more important. Time-varying dynamics can be handled simply by using adaptive estimation techniques. One important example is the dirtiness of the blades, which we are able to track using such estimation techniques. In some cases, a dynamical model is more complicated. For example, a study of wind power dynamics for offshore wind farms shows that a regime type of model is optimal. This is a model where the dynamics are different from regime to regime. An example typically seen for offshore wind farms is that the dynamics and persistence in the wind speed depends on whether a rain event is approaching. Aggregation or upscaling from a set of wind farms with measurements to the total wind power production in an area is typically done using a model for upscaling. Such a model can describe the fact that the wind turbines with online measurements typically are newer and larger than turbines without real-time data for the production. A number of power forecasts can be weighted together to form a so-called combined forecast, which is better than the individual forecast. The combined forecast can be obtained using parallel configurations of the forecasting tool using input from different meteorological forecast providers. By using 2 to 3 different meteorological providers, we often see 10 to 15% improvements in the forecasting accuracy. Forecasts are typically needed on different timescales, from minutes, maybe even seconds, to days. Furthermore, forecasts are needed on single turbines or wind farms to large bidding zones. For large-scale integration, forecasts on various spatio-temporal resolutions are typically needed. If the forecast provider is providing forecasts on varying time resolution and horizons, for instance both hourly and daily forecasts, the individual forecasts can be improved by reconciliation of the different forecasts. Consider, for instance, forecasts of the electricity consumption on hourly resolution, and at the same time daily forecasts are also constructed. Then it's clear that the sum of the 24 hourly consumptions should correspond to the daily consumption. In a study related to a forecast of the electricity load in Sweden, we have seen 20 to 50% improvements by a joint consideration of hourly and diurnal forecasts. Please see the provided references. It's very important to use a forecast provider which is able to generate joint forecasts of wind and solar power generation, and preferably also jointly with load and price forecasts. These forecasts should also use the same set of meteorological forecasts as input for all the models. It's very important also to use reasonable and well-defined methods for comparing the forecast accuracy of the different tools. A set of such methods for point forecast is provided with the references.